Hello everyone, I hope all of you are having a great time at CVIP 2018. I am Sadman Sakib Khan and I am here to present the paper 113. The title of our work is Object Leveling in 3D from Multiview Scenes using Gaussian-Hermite moment-based depth map. So here is the outline of my presentation. First I'm going to describe the problem, then I will go through some of the related works. Then I will introduce you to our proposed approach. Then I will discuss about the experiments, the database setup, comparing methods, results, and finally I will conclude stating some of the future scopes of this work. So why object leveling in 3D? It has some groundbreaking applications in complex robotic tasks, geographical mapping, autonomous driving, medical science, gaming, virtual reality, and many other fields of science and technology. So we have this problem at our hand where we will be leveling objects from a video, and we will create a 3D environment or 3D modeling of this scene that is captured from the video. So these videos are captured in a certain manner. They are captured from different angles, and we thought we can use the depth information along with this RGB frames, and then we can extract features from them, and we can train our machine learning model with these two features, and then finally we can score a 3D map so that we can label objects in them and create a 3D model of that specific scene. So this problem has been approached from different techniques. There is this laser-based 3D detection which suffers from poor resolution, and there is this purely shape-based leveling. It's really successful on large architectural elements, but less so on small objects. Then there was this image only object matching, which can work really well for textured objects. And finally there is this very popular CNN based approach on 3D point clouds, but this approach requires huge data sets. So the motivation of work was in some of the recent studies in the literature. We have seen the depth information play a crucial part while detecting objects of different sizes and shapes. So a robust depth estimation technique can be implemented for this, which will give accurate information of a scene regardless the lighting condition, viewing angle, shapes, and sizes of the objects. So these are the main contribution of our work. We have introduced a focus cube-based depth estimation from Gaussian-Hermite moments of neighboring pixels. Then we have adopted two sets of histogram of oriented gradient features, one from GHM based depth map that we will be calculating, and the another one from RGB frame which is obtained from the video. Then we have implemented one SVM based classifiers to create level probability map, and our approach is object versus background approach. So we will be scoring if a certain point is object or a background. So why have we chosen Gaussian-Hermite moments? Traditional methods of depth estimation use visual cues such as motion, geometry, defocus of an object in a scene. These are limited by shape of the objects and their relative distances. Depth from Kinect is obviously a viable option because there are so many Kinect camera available now in the market, but it suffers from accuracy. So we have chosen Gaussian-Hermite moments because the quality factor of the frequency window of Gaussian-Hermite basis functions is better than other moments. Zero crossings of the Gaussian-Hermite basis functions are distributed more evenly. So these things ensure superior image reconstruction capability, and the noise trovus features of these GHMs are really noteworthy. So this is our proposed approach. First we take an RGB video frame, then we estimate GHM based depth map, and then we extract hawk features from it, and then finally we calculate the depth feature vector, and exactly the same way we calculate the intensity feature vector from RGB video frame by extracting hawk features. Now this is the GHM based depth estimation technique. Let IWIJK be a pixel intensity which is selected by a n by n square shaped window, and DIJK be the corresponding depth value. So we can calculate the focus Q of that specific pixel by using equation 1, which is the ratio of high pass and low pass components of that specific pixel. This gamma term balances between the boundary of high pass and low pass components, and these two components can be found by using equation 2 and 3, and by equation 4 we will be calculating the Gaussian-Hermite moments of order PQ, and this HP hat and HQ hat are the Gaussian-Hermite polynomials, where the sigma is the spread parameter of these polynomials, and finally using equation 5 we will be calculating our depth map. So after calculating the focus Q, there will be some sparse points where the focus Q are not specifically mentioned, so that's why we will be using a matting process. L in this equation 5 is this Laplacian matting process, so that the depth map is getting smooth over the entire region, and this lambda in equation 5 balances between the sparsity of focus map and the depth map. So these are the results of our estimated depth map. You can see in our estimated depth map, the edges are well defined compared to the depth from Kinect, and this will give us better feature vectors that we will be using to label our objects. So this is the final step. After creating the complete feature vector, we will feed them into our SVM based model, which will be scoring which will be predicting if a certain point or pixel is object or background. So after all these scorings, we will be creating a probability map out of the scores using plot scaling, and then using RGBD mapping algorithm we will be creating a 3D visualization of this entire scene of the video. So we have used this RGBD object dataset, which contains 250,000 segmented RGBD images of 300 objects in 51 categories. 8 multi-view videos with different number of objects are in the database, and 11 background videos without any object are there. So this is the setup for training our SVM classifiers. We have used 25 objects in 5 different categories, 11 background videos. For estimating focus Q of a pixel, the threshold gamma is chosen to be 2. The regularization term lambda in the matting process is chosen to be 0.002. The 8x8 window has been chosen while calculating hawk features. Histograms are encoded into a 108 dimensional vector. Parameter alpha is chosen as 0.1, and the MeshLab version 1.3.3 is used for visualization. So we have compared our methods with the two others, one of which is Kinect based leveling. It's very fast in terms of getting the depth data, and the other one is defocus based leveling. It's a very well-known technique for estimating depth and gives pretty accurate values. So we have compared our method in terms of precision recall, average precision, and F1 score. So these are the results of our labeled scenes. We have tested our model in 4 situations. One of the scene is meeting room, kitchen room, office room 1 and 2, and as you can see, our scenes are pretty well labeled. The green thing is a cap. The coffee mug is in yellow, the soda can is in cyan color, and the bowl is in red color, and the cereal box is in blue color. So if we show you a particular scene, suppose the scene 1, a meeting room scene, from different angles, you can see the two yellow coffee mugs are in the same line, but what you can notice here, that occlusion of viewing angle has very little to no impact on our leveling performance. So this is an illustration what our model does. On the right there is a scene of an office room, and you can see that our model has very accurately labeled all the objects of this video. So if we can compare in terms of precision recall, our methods show very constant performance in terms of precision while we are increasing recall. The blue dash line shows the performance of our depth from GHM based technique, which shows superior performance compared to the depth from defocus and depth from Kinect, which are in magenta and red respectively. And these two scenes also show pretty similar results. So in terms of average precision, our method works quite well in all the 4 testing scenes. So we achieve average precision as high as 93.29%, and the performance is better than the compared to ones. So these are the results in terms of F1 score, and as you can see, it's just like the average precision one. We achieve as high as 74.46% F1 score using our method in all the scenes. So what we can observe from these figures, our method shows an improvement of average precision as high as 29.5% and 26.9% as compared to the depth from defocus and depth from Kinect based methods respectively, which is a large margin. And in terms of F1 score, our method shows superior performance too. So in this problem we have used a depth estimation technique that gives us a very robust leveling performance. And so what we can do in future is we can extend this work to level non-stationary objects. That means in a certain video the objects will be moving, unlike this data set where the objects were static. So this will be challenging, and we are looking forward to that one. So thank you all for listening to this presentation. If you have any queries, then please send them to us. Thank you.